Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. Alright, I hope everyone is doing well. Alright, so today I'm going to share about conventional amplitude modulation. Okay, so previously we have learned on double sideband, suppressed carrier, amplitude modulation. Okay, so for the conventional AM, okay, what we do is we just add on from the DSBSC with a carrier. So the difference will be there will be exist a carrier in the modulated signal. So in other words, a portion of sinusoidal carrier is added to the DSBSC. Right, so why they do this is to simplify the demodulation process. Alright, so we can measure the conventional AM by multiplying, just now this is the part of the SBSC. Okay, let me, okay, so this is the DSBSC part, and this is the additional carrier part. So this is the difference between the DSBSC and conventional AM. So when we simplify this equation, it will become AC plus ST multiplied by cos 2 pi FCT, right? But in detail, they want to differentiate the level of modulation by multiplying MA in the signal message or the original message or the information. So after some research or improved way, so they modify the conventional AM as AC multiplied by 1 plus MA multiplied by SNT, which is normalized message signal, and cos 2 pi FCT. So we shall remember this equation for the conventional AM. So how we find normalized message signal or SNT is by finding the signal ST divided by the minimum value of the ST. So for example, if we have a signal, okay, this is X, this is Y, okay, so this should be a straight line. Okay, and then we have a signal, let's say cos and sine is plus, okay, right? So how to find the minimum ST is this one, yeah? This is what we call minimum ST. Okay, so how you get this one? By plotting the signal ST. This is ST. Okay, so if you are taking labs, so what are the criteria that I want you to identify is the minimum ST and SN. So by plotting ST, you will get the minimum ST, and from that value, we got normalized signal, right? Okay, so this is a message signal SNT. For example, normalized signal means the signal ST is divided by the value of minimum ST. So you get normalized SNT, right? Then if you multiply or modulated the SNT with a carrier using MA equivalent to 0.5, you will get this kind of result, okay? But if you are using MA equal to 1, you will get this kind of modulated signal, AM. Okay, and if you do over modulation by using MA equal to more than 1 or 1.5, you are going to get the envelope distorted. So the perfect one is MA equal to 1, but it's actually depends on the value of AM and AC and also the minimum SN, minimum ST. Okay. Alright. So what is modulation index? MA. Okay. MA is only exists in this conventional AM. Okay. So the parameter MA will determine the extent to which the carrier has been amplitude modulated. So it will shows is it over modulated or under modulated by this value MA. Okay. So this MA is defined as minimum ST. Just now I have shown how to find minimum ST divided by AC. AC is the amplitude of the carrier. Or if you don't have this value, you can use the maximum and minimum XAM. Okay, the amplitude, the modulated modulated signal, finding its amplitude Amax and Amin. Okay, so if given to you Amax and Amin, you can also find the modulation index, right? Okay, so from the figure previously, we observed that the envelope of the modulated signal is always positive and will retains the shape of the message signal in the condition of MA is less than 1. Okay, if not, it will be overmodulated. Okay, therefore, the message signal can be easily recovered from the modulated signal by using a simple envelope detector, because you can detect the original signal or the message signal at the envelope. Okay, if you see this one, this is the message signal. Okay, so it more or like the same with this one, the modulated signal. The message is located at the envelope. Okay, so this is MA equal to 1. It perfectly same with the signal. Alright, else this one at the envelope, they have extra message. So be careful with the value of MA, okay, modulation index, as well as this one. It is almost the same, but it's not as accurate as MA equivalent to 1. Right? Okay. After we find the modulated signal, we always have to find the spectrum of the conventional AM. Okay, so for conventional AM, it is the same as the previous Fourier transform conversion, where if we have this one is the first part of the AM, and then this is the second part of the AM signal. Okay, so remember this is looks like or same with the SB signal, and this one is the carrier. So what we do now is we convert the cos to delta. This is the Fourier transform. Right? So when we have 2 pi fct, so the delta will f minus fc, and of course we have this AC divided by 2, because cos will be changed into 2 delta, each will have half of its amplitude. And one more, don't forget, is AC MA divided by 2. Why? Because this cos also we have to divide into whatever the signal Sn minus Fc and plus minus Fc. Okay, so that means whatever the signal will be shifted by minus Fc and also plus minus Fc here. Okay, when we see this extra, okay, from the DSB signal, we'll see an impulse, because delta is an impulse at plus minus Fc, so it will represent the carrier. Okay, so this will present the carrier at the modulated signal spectrum. Okay, so actually it is wasted because it is shows the carrier information, not the message information. Okay, so the message information is conveyed in the sideband of the AM signal spectrum, which is this one. So this one will represent the message signal. This one represent the carrier. Okay. Okay. Note that also the spectrum of conventional AM occupies twice the bandwidth of the message signal, because as we know that if you use this directly uh, multiplication of cos with the signal, it will be double the bandwidth. All right. So this is the spectrum of the conventional AM. Okay, for example, we have the message signal in the form of this triangular. So bear in mind, this is the signal. Okay, the signal is a triangle. Okay, when we convert it into conventional AM, the amplitude will become AC divided by 2. Okay, and this signal will be shifted to FC and minus FC. And bear in mind, there is also a carrier component or delta F minus Fc at the modulated signal. Okay, right now we are talking about conventional AM, so which will be occupying double the total bandwidth. So this is we call upper sideband, okay, and this is called lower sideband. Okay, this is upper and this is lower sideband. So all this information will depends on the message of the signal, but it will located at the FC and minus FC. Okay. All right. Let's see this example. Just put a general AM cos 2 pi FMT. So this message or information is in the cos, and the carrier is also cos AC, amplitude of the carrier, cos 2 pi FCT, frequency of the carrier. Alright, and then determine and plot the spectrum of the conventional AM. Alright, so I think we have done this in the SBSC, but right now we want to see the difference in conventional AM. Okay, so in this example, they have given to you the SNT as cos 2 pi FMT. So that's mean that the minimum ST is the AM. Okay, so right now we just use this SNT in the equation. Okay, so in the equation AC multiplied by 1 plus MA, this is the SNT. Okay, SNT. And this is the carrier. Okay, so we expand the equation. So AC cos 2 pi FCT is the information of the carrier, and this one is the amplitude of the message modulated signal, and this is the cos 2 pi FCT multiplied by cos 2 pi FMT. It will become cos multiplied by cos using the formula cos multiplied by cos. The first cos FC plus FM plus, if it is cos also FC minus FM. Okay, whatever it is, this one will generate 2 delta and this one will generate 2 delta, and there is this one also 2 delta. Okay, and then this one is modulation index AM divided by AC. Okay, so because here they're given to you the minimum ST as AM, so AM divided by AC is the MA. Alright. Okay, now we are going to convert this signal into spectrum. Okay, as I said just now, the carrier part will get 2 delta. This is the carrier part. Okay, so where this is located, minus FC and plus FC. Minus FC and plus FC, this is the carrier. Okay, and what is the amplitude? AC divided by 2. AC divided by 2. Okay, so this is the first 2 delta. Okay, the second pair of the delta is at FC plus FM and minus FC minus FM and plus FC plus FM. Okay, this one and this one. Okay, and the next one is minus FC plus FM, minus FC plus FM and plus FC minus FM, this one. Okay, with the same amplitude MA AC divided by 4. Okay, this one is the amplitude of the next delta. So this is the spectrum of the conventional AM, right? Alright, so how about the power content of the conventional AM? Alright, so we see just now that to find the power in the SBOC is AC squared divided by 2 multiplied by the power of the signal. But for the conventional AM, we add on this amplitude of amplitude for the measurement of the power from this information. Okay, so this one and this one, ACMA divided by 4 multiplied by 2, because there are two signals, and also it depends on the power of the signal. Okay, so now we have also the power or modulation efficiency, where we can calculate by measuring the signal power divided by the total power. Okay, and then this is the formula also for the power peak envelope power. Okay, okay, next let's share this problem 4.3. So just now it just have a general general representation. Okay, the next one we have real number, where the signal is a combination of 2 cos 6 pi t plus 5 sin 10 pi t. Alright, the carrier is 100 cos 1000 pi t. So this is AC. Okay, so the AM is, you have to find the average from 2 and 5. Okay, so I'll show you how to find the average, just like usual calculation. Okay, so the modulator operates with the modulation index of 0.7. Okay, so this is the value of MA given by the modulator. Okay, that means the modulator can tune from any number 0.1 until 1 or more than 1. Okay, so right now they set it as 0.7. Okay, so from MATLAB, the minimum ST is 6.9412. Okay, how do I get this? Is by the you simulate the 2 cos 6 pi t plus 5 sin 10 pi t in the MATLAB. Okay, so let's say this is the signal, but bear in mind this is a absolute value. Okay, so this one 6.941. Okay, if it's negative it can be absolute value plus. All right. Okay, so write an expression for the modulated signal, which is XAM, and also the spectrum. Okay, so you have to find the XAM and the spectrum. Okay, so since it given to you the minimum ST, now you find this SS and T. Okay, that is the first thing that you have to identify for the conventional AM, because we need this value here. Okay, now we substitute the equation. This is AC, 1 plus this is MA, okay, multiply by SNT. Okay, this is an SNT, and lastly you have to multiply with the carrier. Okay, this is the carrier. Okay, this part only, yeah. Okay, now you have all the information. You do the multiplication of cos and cos. Okay, cos and cos. Also sine and cos. Okay, cos and cos will triggers 2 delta, and sine and cos also 2 delta. Okay, so this is for the carrier part, FC, and then this is for the MASNT multiplied by the cos 2 pi FCT. Okay, from here to here. Okay, so basically you have to play around with this value and this value. That's why you have this number 503 and 497, and also this value and this value for this number and this number. Okay, all right, so then we have 1 2 3 4 5 6 7 8 9 10. This is the carrier 1 2 from here, 500 and 500. Okay, so we have 10 delta, yeah? And then 5 plus 503 and minus 503. And then 497 couples with 503. And then we have with the amplitude 25.2 divided by j, or it can be the absolute value 505 and 495. 505 coupled with 495. Okay, so be careful with the all the delta values and also amplitude. So this represent the frequency. Okay, and this one represent the amplitude. Okay, in absolute values. Okay, so for the demodulation of conventional AM, we can use either envelope detector and a filter. Alright, so what we do, this is the example of how to find an envelope detector. Okay, this one, and also this is the design of a RC filter. Okay, so this is the basic filter using RNC. Okay, if we combine this one, the envelope detector and a filter, okay, what we do is we detect the values at the envelope of each of the modulated signal. So we detect the value of the envelope. So what we got here is equivalent to the information or ST. Okay, so that is how the conventional AM demodulated. Okay, so we receive the XAM. Okay, using the envelope detector, we will get the VCT, and then after low pass filter, to remove the unwanted frequency, we will get the original signal back, demodulated signal, right? Okay, so this envelope detection are usually for the conventional AM. Okay, it does not require generation of coherent carrier like the SBSC. We have coherent carrier. Okay, so it just using the simple hardware, diode, resistor, and capacitor. Okay, and it also work with suppressed carrier modulation system if the receiver inserts a carrier. What does it mean? Because we know that in the AM, it will also carry FC. So if we can have a suppressed carrier to work with this envelope detection, or we put this value of the carrier, so we suppress that number or that FC, it can be removing the value of carrier and we can get the original signal. Alright, so this week our lecture until here, conventional AM. I hope you will understand and can also do your lab work. So we continue on next class. With that, I finish with Tasbih Farah, Subhanallah, and also Wal As. Thank you very much for listening.